Good day, all.
How's it going?
Still sleepy.
Yeah.
Apparently so sleepy that I lost my train of thought while describing how sleepy I was. Anyway, how y'all doing? And does anyone have any questions, needs, concerns, etc. before we get started today? All right. So, last time we began talking about the notion of work. This is sort of an application of the forces that we've been talking about. The idea that when you exert force on an object and the object successfully moves as a result of your efforts, that you are doing work on the object, imparting energy into it. This means that every time you exert force or do anything, really, it takes up a certain amount of effort, it takes up a certain amount of energy. And we were working through this formula, describing how to utilize it and what work means. To quickly go over the formula itself real quick again, work equals force times displacement. In order to do work on something, you have to exert a force on it, and it has to move some distance as a result of the force that you exerted. Again, every time you do anything, be it moving your limbs or even blinking or breathing, there is some force and something is moving as a result of it. So literally every single action you undertake, conscious or subconscious, involves a certain amount of work. It involves a certain amount of energy being used up. Work is measured in joules, and joules is the metric unit for energy. It's similar to and can convert into other units of energy like calories. Again, you eat food calories, your body uses that energy from the food to do work, so same concept, just a different unit. Force is still newtons and displacement is still meters. And the additional symbol in the formula, those two parallel lines, represent that the force and the displacement have to be parallel to each other for this formula to work right. Because if you push something to the left and it moves to the left, you're the one accomplishing that task, you're the one imparting energy into the object. Whereas if you push something to the left and it moves up, you're probably not the one doing that. Any questions from last time regarding the formula or the concepts that we addressed before? Okay. Now, before we move on, I want to define an additional term for you guys, because I've been throwing the word energy around a bit, and I haven't actually defined energy for you in the full terms of how we're going to use it in this class. So I want to do that now. Before I show the definition of energy, I want to ask you guys, when you hear the word energy, where does your mind go? How do you try to define or describe the concept of energy?
I think of like effort or power to do something, like the amount of power to do it.
Very good definitions. In fact, that's exactly what the notion of work is as we've been calculating it. So that first thought that you had absolutely applies to the notion of work. And work is specifically using up energy. So you have a certain amount of it in your body in order to do stuff with. You use that energy up, you give it to other objects, because if you push on something, you are taking energy from your muscles and sending it into the other object to get it to move. So all those tasks use up energy that you have and either spends it or gives it to something else. Absolutely phenomenal translation of the concepts that you're familiar with. Now, work is using energy, but what is energy itself? What is the actual energy? If you were trying to actually define the energy itself, rather than just the use of energy. It's kind of a hard thing to describe. And it's not that I want it to be a hard thing to describe, it's just that it is. And I've been studying physics for a long time, and I am sorry to report that the best definition for energy that we have as physicists is it's something that lets matter do stuff. It's kind of hard to define energy itself because you can't really see it. Energy is just something that matter has that can be used to do things. And every time you've ever thought you've seen or witnessed energy, you've technically only seen what happens when matter has energy. You've never actually directly noticed energy itself. So let me ask a slightly different question. When you hear the word energy, where do you think that you see or encounter energy on a daily basis?
All the time.
Can you give me, you're right, you are correct. Anything specific? Like what do you look at and think, there's energy there?
Running.
Running, okay.
Electricity.
Okay, running and electricity, two great examples. When you see someone running, do you see their energy?
No, we just see it being used.
Correct. You see the person using energy and moving. Electricity, that's another good example. Now, when you see electricity, technically, you aren't actually seeing energy itself. What you're seeing, I'm going to switch to a different set of notes real quick. When you see electricity, and frankly, whenever you see anything glowing, for me, this was the primary example growing up, you're not actually seeing energy itself. All of these visuals have some physical, matter-based explanation for what you're actually seeing. In the case of electricity, as the more realistic example, what is electricity physically made of? Okay, yes. The body of electricity is actually plasma. If you haven't heard of plasma recently, it's the fourth state of matter. It's what happens when gas is supercharged and superheated. The sun is made of plasma, for example. And whenever you run electricity through air, because remember, the sky is not empty space. There's air up there. Whenever you run electricity through air, energy from the electricity gets into the air becomes energized, and when air has energy, it turns into plasma and glows for a split second. This is why light bulbs work. All the bulbs above you right now, the long tube ones, literally it's just a tube full of gas that electricity gets shot through, and the gas glows as a result of that. Now keep in mind, what you're seeing then is light given off by plasma, not the actual energy itself. What you're seeing is air that is glowing, like the surface of the sun. And it only lasts a split second because the actual electricity, the physical electrons that make up electrical current, like the electrons that go through the air out of the sky, those only remain there for a split second, and you can't even see the electrons themselves. Has anyone seen an electron with their eyes? Without, say, the aid of the world's best microscope? No. You can't actually see the energy. You can't even see the electrons. All you can see is the physical matter of the air glowing because it has energy. And again, if you watch the same shows I did as a kid, same basic thing here. Whether it's Super Saiyans or even like magic on various fantasy shows and movies, what you're technically seeing for like force fields and all that magic stuff when Dr. Strange does his thingy, technically, probably, that is air with energy in it that is glowing as a result. Granted, Doctor Strange is a wizard, so literally it could work very differently. But best understanding that I have, air with energy. You don't see energy, you see what happens when matter has energy. Again, the energy itself, incredibly mysterious and hard to directly observe. Because you only ever see it when something has it and is doing something with it. You only really see what it does with the energy. When air has energy, it glows. When a person who's running has energy, they move. When you possess thermal energy, you are warm. That sort of thing. What we know, because it's so hard to actually observe the energy itself, I'm going to try to define to you the things that we do absolutely know about energy so that we can use those definitions to help us describe our work calculations. The things that we do know about energy: matter can possess it, matter can use that energy to do stuff, and the energy can be transferred between objects, transformed between various states of energy, and used to do tasks. And in fact, multiple of those things tend to happen at the same time. For example, when you throw a baseball, where's my piece of styrofoam? When you throw a baseball, before you even start moving, there is chemical energy stored inside of your arm, inside of the muscles in your arm. Chemical energy is one of the forms of energy. That's the form that's in the food you eat. It's stored in bonds. You eat the food, that energy is now stored inside of you, and your muscles can break down those bonds to release energy to allow you to use it. So, before you ever start moving, there's chemical energy in your muscles. When you start moving, your muscles go through the process of breaking those bonds, releasing the chemical energy into a mechanical, kinetic form. Kinetic energy is what allows things to move. So, your arm begins creating kinetic energy, so that's a transformation process. Your arm creates kinetic energy, and now that your arm is moving, you're able to do work on your baseball by exerting a force on it as it moves a distance. So that's the work formula there. Force times distance. That's how you throw anything. And in doing that, when you do work, I am then transferring energy into the baseball. Now the baseball has energy, and now it moves. So that was a transformation from chemical to kinetic in your arm, and then a transference as I did work on the ball to throw it. So the act of work is the act of any combination of using, transforming, and transferring energy between objects. Not only does every single action you take involve using some amount of energy, it also, again, involves a transformation of that energy. Because your body tends to store energy in the chemical form that it was when you ate it. And then when you use it, that chemical energy is released to let you actually move. How do you feel so far? Okay. I would like to demonstrate we're going to apply the work formula to a scenario so that we can describe the work that friction does and how that friction is transforming energy in this case. So, here we have a 12 kilogram object being pushed forwards at constant velocity with a force of 62 newtons. The box slides a distance of 5 meters during this experiment. So, pictures are always helpful. here we have our 2 kilogram box, 62 newtons being used to push it forwards. I don't know why, but I've described it this way as forwards today. And the box is going to move 5 meters in that direction as a result of our efforts. I've got the things that we know written over here: mass of 12 kilograms, displacement of 5 meters, and an applied force of 62 newtons. So, first question, what is the force of friction that's going to act on this box?
$62 newtons.
It is 62 newtons. So, correct assumption. Why is it 62 newtons?
Because it's moving at a constant velocity and is being pushed with 62 newtons this way.
Excellent, exactly correct. Constant velocity says what about the box's acceleration?
It's not going anywhere, it's 0.
It's not accelerating. Acceleration is 0. And Newton's second law reminds us, if acceleration is 0, net force is 0. Therefore, all the forces present must add up to 0. And, bless you. Bless you again. If the box is moving forwards, force of friction will automatically spring into existence to try to push the object backwards instead. So, within the x-axis, these would be the 2 forces affecting the box's motion. Those are the 2 forces that would add up to our net force of 0. So, net force in the x-axis is going to equal our 62 Newton applied force forwards plus force of friction backwards, and they must add up to 0 because the box is not accelerating. If 2 things, specifically only 2 things, add up to 0, they must be equal and opposite to one another. So, correct. In this case, the force of friction attempting to stop the box is equal to 62 newtons backwards. This is always the case for objects moving at constant velocity. So, a tip that you can hang on to, if an object is moving at constant speed, not accelerating, the force pushing it forwards would be equal and opposite to the force of friction trying to slow it down. As long as they're balanced, you maintain equal speed. It's when they're imbalanced that things either speed up if friction is weaker than the forward force, or slow down if friction is stronger than the forward force. I'm going to compare this again to a car that is driving. If you take your foot off of the gas pedal, what happens to the car's speed?
It's going to slow down eventually.
It's going to slow down. That's because the force of friction is literally going to push it backwards and force you to accelerate. And that's why you will eventually come to a complete stop. When you turn on cruise control in your car, the car's, one of its internal computers automatically calculates how much force does it need to add to the wheels to keep the car moving forward at the same speed. So every time you turn on cruise control, your car does this math for you so that the force forwards equals the force of friction backwards and you remain at constant speed as best as it can maintain. So, once again, assumption that you are generally very safe to make. Constant speed means friction backwards and force forwards are equal. Stay hydrated. So, 62 newtons backwards, I've written it as negative just to oppose forwards, is our force of friction. Questions arriving at that number, what it means? All right. Next question, how much work does friction do on the box as this happens. Now, all forces are technically capable of doing work. The main caveat is that the force needs to be parallel to the axis the object is moving in. Now, last time we looked at a case where something was moving to the left, and we looked at how much work gravity does on it. That's not the same axis. Those are perpendicular, so gravity is not doing any work while something moves sideways. However, this box is moving sideways, and friction, even though it's in the opposite direction, is still in the same axis. So even though it's negative, it still fulfills this requirement. So, the work done by friction equals the force of friction times the box's parallel displacement. It doesn't actually matter where the parallel symbol gets written. As long as it's there, the two variables have to be parallel to each other. So here I'm just reframing the formula a little bit to describe work done by friction in terms of the force of friction. Friction is absolutely capable of doing work. And we're just going to talk about what it means when friction does work. So, work done by friction. Our force of friction is 62 newtons. Our delta x is 5 meters. And it's important to note the 5 meters is forwards. The box is moving forwards. The 62 Newton friction, again, we're describing friction here, not the force that is being applied forwards. The friction points in the opposite direction, same axis, but opposite direction as the 5 meters forwards. Same axis, but because of the change in direction, we do still need to note that frictional force is negative because it's in the opposite direction of the motion, as friction always is. It's always in the opposite direction of motion. This is going to give us a negative answer, a negative amount of work done. Namely, memory serves, negative 310 joules. Friction always does negative work for that reason, because friction takes energy away from things. When we do work to throw something, like when I throw my styrofoam baseball, I'm exerting a force on it in the same direction as motion, so those would be two positive numbers, and I would be doing positive work on the ball to give it energy, to successfully impart energy into it. Whereas friction does negative work because it takes energy away. Positive work means you are giving energy to something. Negative work means something is losing energy. So in this case, actually not even in this case, universally, friction is an energy leech. It just steals energy from stuff. It's a necessary evil because without friction, we'd slide around across the ground endlessly. But the main problem with friction isn't even the fact that it stops things necessarily. The main problem with friction is that it steals energy. And when anything does work, friction included, it not only changes what object has the energy, it can also change what form the energy is in. Off the top of your head, what are some of the forms of energy you can think of? Energy is malleable like matter. You have solid, liquid, and gas for matter. Energy is malleable in that it has lots of different forms that it can occupy too. Off the top of your head, what are some common forms of energy that you can think of? Or that you remember from me mentioning a second ago? Kinetic, very good. Kinetic energy is the energy of motion. If you've ever seen something move, it's because it has currently kinetic energy.
Chemical.
Chemical. Very good. As stated earlier, this is the form that is in your food, and therefore the form that is in your body until you use it. But technically everything, all molecules, have chemical energy stored inside of them, and breaking those bonds releases it, like with fire and baking soda volcanoes.
Potential energy.
Very good. Now, potential energy, I'm going to actually put that over to the side here, because that's kind of a blanket term. There's lots of different types of potential energy, because that's just an extra label tacked onto any form of energy that is currently in stasis to be used later, if it's stored like in a battery. Again, the chemical energy that's in your body is, for the most part, potential chemical energy. Food is chemical potential energy because the food's not using it. But when you eat the food, it's then still stored in your body as chemical potential until those chemical bonds are broken and the potential can be used for something. Namely, kinetic energy, because to do anything, your body has to move some part of you. And as long as something's moving, it has kinetic energy. So on the other hand.
Plasticity, maybe?
You know what? There is technically a form of energy called elastic potential energy. So as I add potential forms to the list, I'm going to draw arrows from potential over to indicate that those forms are themselves types of potential. And yes, elastic potential is a thing. Whenever you throw a turbo bouncy ball at the wall or something, for a split second when it hits the wall, it squishes, and all the kinetic energy it had stored becomes elastic potential energy for a second. That's energy that's stored inside of it, because it's not actively moving anymore, it's just stored for the moment you freeze frame on it hitting the wall. And then when it bounces back off, that EPE turns back into KE and it's allowed to move again. All elastic objects do this. It's why you can pull back on a rubber band to store energy in it and then fling it to let the energy go. Excuse me. Any others?
Thermal.
Thermal. That's the main one I definitely wanted to mention. Thermal energy, it is a form of energy, and when you have thermal energy, you're warmer. When you don't have thermal energy, you're colder. So, fun fact for now, we'll talk more about this in the thermodynamics chapters. Cold doesn't exist. Cold is the absence of thermal energy. So you are either hot or you're not hot, physically speaking. So cold is the absence of warmth. It is not the presence of coldness. You can't keep the cold out, you keep the heat in. Now, thermal energy, it's everywhere. Every object has some amount of it, and whether or not you have a lot of it just determines if you are very hot or less hot. And thermal energy is kind of pesky because we do need it to stay alive. Your body does create a certain amount of thermal energy because you are a warm-blooded mammal. But thermal energy is pesky because when friction does negative work to take energy away from things, it not only transfers energy by taking energy away from the box, it transforms the energy it steals into the thermal state. You know, I've mentioned a few times that this warms your hands up, right? That's because, again, literally of friction between your palms. When I do this, friction does work to take kinetic energy away from my hands, slowing my hands down. And it doesn't stay kinetic energy after friction steals it, because if friction kept energy in the kinetic form, the desk would start moving. Because if it still had kinetic energy, the desk would be moving around. Instead, all the stolen energy becomes in the thermal form, which is why your palms warm up. It's why tire tracks on the road are warmer than the surrounding dirt. Frankly, just the road in general. Like when cars run over highway, the highway is warmer than the surrounding dirt. And, wait, what was my next point? I lost it. Oh, It's why everything, machine, organic life form, etc., overheats. Your body's designed to be a certain temperature at any given moment, or within a certain range of temperatures. And that's true for machines as well. They have certain temperatures they're designed to operate at. But any time you turn a machine on, whether it's electronics or your car, or again, the machinery of your own body, every single time some part of that moves, there's going to be some amount of friction, because you can't escape it, which means friction's going to create a certain amount of thermal energy. Friction's always present, and it's always leaching energy into the thermal state. So your car has a coolant system in the engine because, well, for one, there's literal explosions going on inside of the engine cylinders, but two, as all of the pieces of the engine move past each other, they're going to generate more heat because of friction, and eventually the engine just keeps heating up until it breaks, melts, or both.
It's not pretty.
It's not pretty. I have not personally seen an engine block that's had all of its parts melted and fused together, but it would be a massive pain.
I'll send you a picture when I get to work. Okay?
Yikes.
I blew one up Friday.
It's honestly the same inside of computers, because even if you don't think electronics have many moving parts, technically electricity is matter, because electrons are made of matter. Electricity has weight, that's a weird thought. Electrons are moving through wires, and there's technically friction involved in that, because they're moving through and past matter. So the electrons leave energy behind inside of the wires and the components of your devices, and that warms them up, which is why your computer and your phone and everything else has a fan in it to try to mitigate that heat buildup. Eventually, the machine will build up heat, overheat, and melt. Same for the human body, because there is friction inside of your own muscles. I'm not a biologist, but the way I understand your muscles is they are made of various fibers and tendons and such, and as you use them, those fibers do move across each other as they expand and contract and slide around. That's generating friction, because anytime matter moves across matter, there's friction. And that means within your own muscles, friction is stealing energy from you and turning it into heat, and that's why you overheat if you overexert. It's one reason why. So, friction's a pest. We need it, but it's causing long-term problems, because every single action you take creates more thermal energy, and so less and less normal energy is available as slowly all of it turns into thermal over time. I mentioned the term heat death of the universe once before. That's what happens when friction steals all of the energy forever. We have a while to go before we get there, but there's a clock running. Anyway, list of energy types. There's frankly even more besides those, but as the semester goes on, we will study most, if not all of them. If anyone's wondering, electricity, electrical energy is another form, although it's kind of a weird subcategory of kinetic, because it's technically electrons moving around, so it's still matter moving.
Would nuclear be a sub of that too?
So nuclear energy is weird in that I'd say nuclear potential energy, like the energy that's just inside of an atom as it standard exists, that's, what was I going to classify that as?
You said potential.
It is a form of potential. You're absolutely right. Oh, I remember now. So nuclear energy is weird, because when an atom fissions, and you actually have nuclear fission to release nuclear energy, or even nuclear fusion, what's happening there is matter transforming into energy. So in a way, matter is itself a potential form of energy. Because anytime an atom breaks down, a tiny piece of its mass transforms into more energy. That's what happens every time an atom breaks down, because if you think about it, nuclear fission, which is not really a part of this class, so this is more fun fact than anything else, When an atom breaks, it's like breaking a physical object, right? You break a stick in half, and the two halves of the stick should have the same total mass as the original stick, correct? But in nuclear fission, that's not technically true. When you rip an atom in half, like say it had 12 protons to begin with, the resulting halves may have between them 6 protons and 5 protons. The other one vanished because it literally broke down into energy, and now it's just gone. And that's why nuclear reactions create so much energy. They literally turn matter into more energy, and it's then radiated outwards in the form of literal radiation. So that's an extra form of energy for you. Radiation itself, which includes light. So nuclear energy is a form. It's either stored as matter or it's actively in use irradiating something.
Did you see how they were talking about doing like nuclear fusion instead of fission?
Yes.
So how does that work?
So I'm going to describe it in terms of how the sun works. The sun is a big old superheated ball of plasma, and it's so hot that the hydrogen atoms that make up the plasma are moving around so fast that they slam into each other at high enough speed to permanently merge into helium. Because hydrogen has 1 proton, helium has 2 protons. So they jam into each other fast enough to get permanently stuck. Now, this is not like normally when you stick 2 things together, you just expect, oh, you add their masses together, now it's one object. Nuclear fusion's weird because, like nuclear fission, it still gives off more energy than it normally had because some part of the original mass still breaks down into more energy. For example, say one hydrogen had 1 neutron, one hydrogen had 2 neutrons. Slam them together, you get helium, but now there's only 2 neutrons. 1 plus 2 equals 2. No, one of the neutrons turned into energy, like how fission does too.
So why do they say that's safer?
It's safer because it does give off energy, but less of it is gamma.
Mm.
You can control it, right?
Yes, you can control it more, and when we do nuclear fission, we tend to break down stuff like plutonium and uranium. And even after those break down, they're still radioactive. Whereas when you fuse hydrogen into helium, that's not radioactive, that just fills balloons.
Okay, that makes sense.
So it's mostly that the waste products are way less harmful. They also are less rare.
Interesting.
It's like we need fusion, we absolutely do. Like nuclear power plants are already the most efficient way we can build energy. And if we were using fusion instead of fission, it'd be even better because then you don't have to store barrels of nuclear waste everywhere. You just have helium tanks. It would be akin to creating a little tiny star that just gives off more energy than it took to create it. Honestly, I'd compare it to Tony Stark's arc reactor.
That's really cool. Mm.
It wouldn't be exactly the same. It'd be huge to start with, but maybe one day we'd have tiny little stars powering all of our cars. We need nuclear fusion. It could end the gas crisis. So, started talking about all this as it relates here. Main things to note, friction can do work. Namely, it does negative work by transferring energy out of whatever was moving, and it transforms energy by turning it into thermal. So, demonstration of work as a method of using, transferring, and transforming energy. And all of our work calculations will involve some use, transference, or transformation. And technically, since you need force to do work, every time you exert a force, you do these things. It's all connected. Now, we're a little light on time, so the next thing I want to do is just define one of these energy types in more detail to give you an equation to be able to use with it. There's two types that we'll focus on this week. I'll just introduce one of them for right now, that being kinetic energy. Namely because it's the easiest form to grasp. You see something moving, it has kinetic energy. You mentioned an athlete running earlier. They have kinetic energy that is allowing them to move. The formula for kinetic energy, the way to calculate how much kinetic energy something has, Ke, there's no other abbreviation than that, it's just a two-letter variable. Kinetic energy is equal to 1/2 times an object's mass times that object's velocity squared. If an object is moving, it has Ke. And if it is not moving, it has no Ke. If you're speeding up, you are gaining kinetic energy. If you're slowing down, you're losing kinetic energy. So ultimately, force, doing work through force is usually the act of giving something kinetic energy, whereas doing work to slow something down takes kinetic energy away from it. Again, that's what friction tends to do. Some things to note about this formula. Ke is measured in joules. All forms of energy in this class will be measured in joules. It's just the unit of energy we like to use. It's the same unit as work, because again, work is the amount of energy used, transferred, or transformed. Kind of like how all forces are measured in newtons, because they are all forces. Mass is measured in kilograms. We want kilograms for every formula. And velocity is still meters squared. Some things to note about this formula. One, notice that this V term is squared and is on the opposite side of Ke. This means if you go faster, if V becomes a bigger number, Ke becomes a bigger number. Going faster takes more energy. Specifically, it takes exponentially more energy because the V term is squared. If you double your speed, you quadruple the kinetic energy requirement of that activity. This is why running sucks. Literally, by speeding up, you exponentially increase the energy cost of moving at that higher speed. That's why walking a certain distance is way less tiring than running that distance. Similarly, your car is less energy efficient at high speeds than at lower ones. Granted, it's really technically less efficient at the highest speed of a certain gear, but at the highest speed of a gear before you switch into the next gear, that's as inefficient as your car gets. So you want to be at the lowest speed of the highest gear, which might not mean anything to you if you drive automatics like I do. But going fast costs more energy. Similarly, M is also here. It's not squared, but it's still important, because if you double something's mass, you double the energy requirements to get it up to the same speed. This is why it takes a lot of energy and a lot of jet fuel to make planes go fast. So, last thing we'll do today. Please quickly tell me, which of these two scenarios has more kinetic energy in it? All right, why do you think A? It is going faster. You're absolutely correct. And as I did say, speed is costly. So let's calculate it real quick. Ke, or say, 1/2. Now that's 5,000 grams. We want that in kilograms, which is only 5. So 5 times 3 squared is going to be, I believe, 22.5. Meanwhile, for a human walking, that's already kilograms, so we don't have to convert anything. 100 times 1 squared times 1/2 is actually 50. So depending on how good your bowling arm is, walking costs more energy than bowling. Questions, comments, concerns, etc.? All right, next time we will do some work calculations to show how energy turns into and out of kinetic energy, and we'll also define another energy type to turn AE into. We do have lab this week, report to lab as normal, and if you need anything, have a wonderful day. Technically, yes. This chapter is very long for some. Yeah. I think chapter 2 will take us the rest of the week. Wednesday we need to talk about GHG, and then Friday we need to